So, hi everyone. I'll be the track owner for the Joy Room. Right now we'll have Pawel Szulc giving the first talk of the Joy Room in the morning. So, Pawel is a Haskell developer by day and a Haskell developer by night. You might know him from a lot of good talks about software architecture, distributed systems, and polysemy. And he will definitely entertain you with getting acquainted with lengths. Please welcome everyone, Pawel. Pawel, please go ahead.
All right, can you hear me, folks? 1, 2, 3. All righty, let me share my screen. Just let me know if you see it.
Yeah, I can see
All
it.
right. Awesome. So welcome, everyone. I am fully aware it's Friday, 9 a.m. at least in Europe, here in Poland. Probably like 50% of you are on stand-ups right now. Hey, let's get this through. So getting acquainted with Haskell with lenses. All right, so this talk is mainly about, well, there are 3 sections in it. So the first one is about what kind of problem lenses are trying to solve. Once we learn the problem, then we can talk about a little bit about solution, how they try to solve the problem, what other nice combinators were born along the way. And lastly, we will spend maybe like 20 minutes trying at least to understand how lenses are implemented. All right, so let's get on with it. So there are 2 things which are fundamentally broken in Haskell. Those are record syntax and strings. And since we only have 45 minutes, we will only talk about the first point, really. Somebody should make a talk about strings in Haskell and about the pain in it and also how to overcome the pain. But let's focus on record syntax. Why does it suck? Why is it broken? Where some quotes, record system is a continual source of pain. State of Haskell survey shows us that multiple people were saying that record syntax is still tedious. And obviously, Reddit, being Reddit, says shitty records. Now, we can actually see with our own eyes how the record syntax is broken. So let me give you an example. We have a conference, a simple data type that has an organizer and a list of speakers. Organizer has a name and contact information, where name is just the first name and last name, and contact information is address and email, where address is street, city, and country. And also organizer conference has a list of speakers, where speakers is a data type, just only holds a single information of whether the slides are ready, yes or not. Okay, so how do we get things from a record? So given that we have here a object representing this data type, organizer, has a name and a contact information, we see that nice little sort of syntax is nice in a way that the name that we use for defining the data type can also be used for constructing it. And by the way, it also acts as a function that allows us to fetch the information from the given object. So I can call the name function, give it an organizer, and give the name back. So here's an example. If I call name Ollie, I will get her first name and last name. Now, this is good, but it actually can be done a little bit better. There's this nice little function operator, ampersand, in data.function. So what it does, it's basically a function application, but just reversed. You first, instead of giving first a function and then the argument to get the value back, you first give the argument and then the function. So as an example, we can call length with some array and get the length as a result. But you could also say the array and append length, and that gives you exactly the same result. Why do I talk about it? Well, because if we apply that operator here, we could say Ollie and a name, and this sort of looks maybe like this little dot that you had in any other language. Okay, I think it's nice, and one of the things nice about it is that it, I don't want to say compose, but it almost looks like Ollie.name.first name to get her first name, right? And you can pretty much build something a little bit more complex. So, if we want to go from a conference to organizer's country, we can say like conf organizer contact address and country, and that works. But unfortunately, if let's say we change our data types a little bit, so now not only the organizer has name, but the conference has name, and the potentially speaker has name. Suddenly, compiler is not happy. We can actually do something about it. So there is something we could do about it. And here you have Eric Meyer praying, oh God, please don't let it be Haskell extension. But unfortunately it is. It's a duplicated record fields. So it means that if you add this pragma to your file, suddenly everything compiles and life is good again. But then you try to write function like that. You just try to use the name. So here I'm trying to get the name of the conference organizers. This should be straightforward. It should be just conference organizer name. But this ambiguous occurrence name hit me one more time again when I just tried to use it. I'm like, oh, God damn it. Well, we can do something about it. There is another extension, which is called overloaded labels. But this time we don't care about Eric anymore. We just go full berserk. We leave the Haskell 98 world and go into the world with all the extensions, because not only we have to add overloaded labels, but we have to add data kinds, because there's like a little bit of type level programming. Well, anyway, you will see. Overloaded labels gives us one single type class, which is called isLabel. And it's a type class that you create instances for your type A and for some particular symbol. And when you haven't seen type level programming in Haskell, symbol is just like a type level string. So just to give you an example, I can create an instance of isLabel, give it a symbol encode panda, and tell the type, the A type is speaker. This means that I have to provide a function from label that will give me a speaker, because the A at this point is a speaker. So I here created a speaker, Pawel Szulc, and his slides aren't ready because my slides are never ready. Anyway, having that, I can call this function from label. I can use type level application to apply the first argument, so the type level argument encode panda, and yeah, I would get the speaker back. There's a nice little sugar notation. So instead of just saying from label and then at and type level string, you can just use hash encode panda. Underneath, the compiler will sugar this into that. So it works exactly the same. It does the same thing. It looks a little bit better. So why I was actually talking about isLabel, how are we going to use that? Well, let me remind you, the problem was we used name. Compiler freaked out because names are defined in that many places. And so now, because we have this defined in conference, an organizer, and a speaker, so we could create an instance of isLabel type class, and this type, the symbol will be just the string name, and the value, the A type, will be a function from organizer to name, and the implementation just saying name is just reusing that name from the constructor, from the data constructor. Magically, this time, compiler does not freak out for whatever reason. He was freaking out a moment ago, where it was obvious which name he wanted to use. But here he's like, yeah, okay, I'm good, I'm fine. So now we can actually, instead of saying conference organizer name, we can just say hash name, and things will compile. So if saying this makes you do that, I don't blame you. But stay with me, because we're not over yet. We still have to learn how to set things with using record syntax. So setting things to a record syntax, well, at the beginning, it's straightforward. So if I have a Haskell of conference, and as you can see, the list of speakers is empty, I think it would be a good idea to have at least a couple of speakers. So here, I can say Haskell of open curly brackets, say speakers, and after equal sign, I can give it a list of speakers. And now, if we fire that, we get a new conference with a list of speakers in. So, okay, so this doesn't really look that scary. Maybe you can work with that. But, well, if we try to do something a little bit more complex, so let's say I want to I believe slides are never ready. Like every speaker essentially is never ready for the conference. It's just the nature of this, evangelism part of being a speaker and software developer. So I would like to have a function that goes from conference to conference and basically change all the speakers so that their slides are not ready even if they thought they were. And yet this is doable. So I can just say conference, open curly brackets, says speakers. Well, this is a list. So now I have to, look at the old speakers and flat map over it and then change slides which are ready. But this, for something that simple, writing that many lines of code is like, ugh. Well, it gets worse. If I want to change the organizer's email, so let's say I have a function modify email that goes from string to string, and I want to give back a function that goes from conference to conference, well, this is already so tedious work. Well, because conference will have a organizer, a new organizer. New organizer is an old organizer with a contact information which is assigned to a new contact. Well, what's a new contact? New contact is basically an old contact with a new email, where new email is a modified email applied to the old email. If that's not imperative programming, and that's not, I don't know what is. We are basically have to describe every single step. I'll forget about boilerplate. This is just, oh. Okay, so this obviously will not work. There's no way this will work. So what can we do about it? Well, there are a few things we could do about it. We could change programming language, but we are already writing Haskell. Most likely we've seen everything else. We know how broken it is. So that's not an option. We could potentially just quit the industry as a whole. I myself, when this whole thing eventually collapsed in 2030, I'm planning to build my own alpaca farm and just move to the countryside. We could ask the Oracle. So let's just do that. Let's ask the Oracle. And the question is there an alternative to records in Haskell? Apparently it is, and it's called Lens, and it's available on Hackage. So Lens, I've created using some available tools on the web. A little bit animation, maybe it will help. So imagine this is a conference. This is your data type conference. You have your conference name, you have your organizer, and you have your list of speakers. Now, Lens is a thing that allows you to focus only on a particular element of that data type. Here I have a lens which allows me to only focus on the organizer. So if I put that lens above the conference, I can just see right now only the organizer. I can change the organizer, modify it from green to red, whatever that is. And if I take the lens back, what I got in return was a new conference with a changed organizer where the name and the list of speakers stay the same. We could obviously have another lens, which would be created for organizers, allowing to focus only, let's say, on the contact information. Now, the really nice thing about lenses is that they compose almost like puzzles. So I have a lens that allows me to focus on a conference, to look just at the organizer. I have a lens that allows me to focus on the contact information from the organizers. If I put those two things together, I get a lens that allows me to focus on the contact information from the perspective of the conference. So if I now put that on my conference, I now only see the contact information in the broader spectrum, in the context of conference. So I can modify the contact information. And if I take the lens back, I get a new conference with a new organizer who has a different contact information. All right? Enough about animations. Let's actually look at the data types. So, by the way, I think I have time till 10. I hope that's true. Yeah, let's say this. So we have this type called lens prime SA. Okay, so when you have a type which looks like that, what it means, and this is the example where you have an organizer, lens prime conference organizer, it means that you have a lens that allows you to focus on the organizer from the perspective of the conference. So how you can use that if you have that lens? Well, you have a view function. So view function will take your lens, will take your conference, and allow you to get that information about the organizer. So here, if we call this function, we get the organizer from Haskell Love. For each normally named function, there's always an operator in lenses. And I would encourage anyone who's learning lenses to just use the operator most of the time, because they are consistent. There's a lot of them. I think there are more operators in lenses than are atoms in visible universe, but there is a consistency in naming them. So once you get the initial idea, it's really easy to guess what the name of the operator will be. So, and this almost looks like a dot in any other language, right? We just say Haskell Love dot organizer, and we have that organizer. As I told you, it would be really nice if lenses compose. And here we have a few lenses, one from conference to organizer, from organizer to contact, from contact to address, and from address to string. We see that they align together just right? It would be nice to have an ability to just compose them together, right? Well, it is doable, and it's doable with a dot operator. You might be thinking, wait a minute, dot? But dot is just it's function. It's a function composition in Haskell. How is that possible that we use that for lenses to compose lenses? Well, it's mainly because it's a clever abstraction, clever way of implementing lenses. But we hopefully will see how that is. So, but for now, we can just remember, right, that we can compose lenses together using that dot function. So I can say Haskell of organizer, that contact, that address, that country, and that gives me a country back, which is great. Also, I could, with lenses, not only view things, as you saw with my cool animation, but also modify them. So there is a set function, which will take three things. It will take your lens, it will take the value that you would like to set, and also the initial structure on which you're working. Here we have a lens that goes from conference to its name, to string, right? So it means that it allows us to change the name of the conference. And as you can see from the example, it works. Now, set has its own operator. So it's that dot and this squiggly little character. I don't even know how to pronounce it. And so now this is just an infix version of set, but we can use the trick that we learned before with the ampersand. And so that means we will take the argument. So previously the argument, the conference, was at the end, but as you know, with the ampersand, we can reverse that, we can flip that. So we can take the argument, put it first, and then after the ampersand, we can give a function. So that eventually allows us to read this Haskell Love name, change to or set to Haskell Love 2020. And that just works. Okay. Well, you remember the lens is composed. We could potentially create a lens from that would go from a organizer to organizer's country, or even further from conference to a country, to organizer's country. And we can compose lenses as we did before with dot, and then we could use the set operator to change the organizer's country, because yes, I want Haskell Love to happen in 2021, and if it's going to be on site, I want this thing to happen in Poland. That's why I'm modifying this. Okay, so nice little getaway from this sort of arranging syntax is that if I would like to modify, let's say, also the name of the conference in one go, I can just say, and name is Haskell Love 2021, because from the first line, we get the conference back. So that conference, we can one more time apply to another lens, and that gives us eventually the conference that has a name changed, and also the country of the organizer in its contact information changed. hopefully that makes sense. This is the nature of what lens gives us. All right. So still, we would like to, we somehow still need to get those lenses, right? So the easiest way, because I only showed you the type signatures, I have not shown you how to get those lenses. So the easiest way to do it is basically use function lens. Function lens, and this is not the true type signature of this function, but for simplicity, just for now, let's say it is. So lens, because lens is just a combination of getter and setter in one data type, we can construct lens providing both the getter, so the function from S to A, and the setter, so a function that goes from the original structure, taking the structure, the focus, and giving us a new structure. That gives us the lens. So yeah, let's try actually to use that. So here I'm just saying organizer, lens, getter, setter. So what is getter? Well, getter can just be the function name organizer, right? Remember when we had the definition of the organizer, and each of the elements in the constructor were actually functions. So organizer is a function that goes from conference to a organizer. This is something we already have. So that is our getter. We could just inline it. The setter will be a function that takes a conference, the new organizer, and modifies the conference, setting the new organizer to O. So that works. But if we try to define a lens for name, we hit back this notorious error because we have so many duplicated record names defined. Compiler freaks out. Well, there is a way to work around it. You could use a little bit of pattern matching and it will work. So let's say it's doable. It's not great, but it's doable. What the problem is that this is just a subset of lenses that we need from our little example, right? But it's already huge. It's already like, oh, I don't want to write this. Could somebody just do that for me? Well, there are two approaches, and let me show you both of them and then select a winner. So the first approach is just to use template Haskell. So in other words, macros. So the way it works is you define your data type, let's say here a ticket, where the names in that record are prefixed with underscore. So you have underscore event and underscore price. If you turn on template Haskell, then you can call a magical function make lenses, which will automatically create two lenses for you. One will be called event, the other will be called price. So here, if I have a ticket, I can view the price, or I can set the event name. Those two, price and event, were generated by template Haskell for you. This is fine, but, well, if I have a data type ticket with event and price, and then I want to create an item because I will be selling stuff during the conference, and the item has an underscore ID and the underscore price, you see we define two prices, and yes, we hit the multiple declaration of price one more time. So template Haskell did not solve that. It solved the sort of the problem of generating those type classes for lenses for free for us, but it still has some issues. And so the way you overcome this is that you have to keep your names unique. You have to prefix them. So you have like an item price, underscore item price, and underscore ticket price. And it's just, wow. There is a second approach using GHC generics. So, and what I mean by that is basically this library generics lens. So the idea is, if we have this data type like conference and organizer, we will have to provide instances of type class generic. We can derive that information using yet another extension, derive generics, which allows us to do exactly that. So it's like, oh, give me a generic representation of conference and give me a generic representation of an organizer. And given that I have that, I can actually call Haskell love, view, and then say field at organizer, field at contact, and field at email. This is better, but it could be better. You remember the extension that we used before, the overloaded labels? We can actually apply that here, and we can just say hash organizer, hash contact, hash email. This is a lot cleaner. There's a lot less noise, and it will be generated automatically for you during the compilation. It doesn't use any macro whatsoever, just the built-in generic functionality from GHC. And the nice thing about it is that if you have two data types that share the same name of the field that they have, you can still use it and compiler will be completely happy about it. So I can say Haskell loved that name or Haskell loved that organizer that name, and it all works. So we've seen at the lens prime that goes from S to A. Hopefully, like you get like what it is by now, and you will be able to use it instead of using prime. The question is, what is really a lens? Well, lens, get a little bit more parameters. So lens prime was from S to A. Lens is from S to T to A to B. So it's lens stop. Now you might be wondering, why stop? Well, the story goes that one day somebody on Reddit yelled shitty records, and Edward Kmet was like, well, hold this, stop. So stop is, we have 4 parameters because we are trying to solve one particular problem. Remember, maybe before the problem, like the idea is here that you have now ability when setting values to change the A to B, and also change the structure S to T while setting things. So the view, the getter stays the same. You have, if let's say conference, well, that's not a good example. I will show you an example in a minute. But you have, the getter stays the same. The setter is a little bit different because you have an ability to go from A to B and from S to T. So if that's weird, don't worry about it. There's an example in the next slide. Just a little bit of notion that lens prime SA is just lens SSAA, which now that I read it out loud, it sounds really wrong. But anyway, this means that lens prime is a normal lens where we don't change the type of the structure and we don't change the type of the focus. We stay in S and we stay in A. So an example. Imagine that I have a lens that I call it's lens prime, and I call it first. The structure here is a tuple from A to B, and the focus is A. So I can implement this, right? I have a lens that gives me ability to fetch the first element from the tuple and set the first element from the tuple. And you've already seen this, right? I can call for the first element, I can view it, I can set it. But if I try to, change the type while setting it, if I want to say, well, this is no longer a tuple of, let's say, 2 integers, it's a string and integer, or a num, to be more precise. The compiler will tell us, well, this is impossible because I cannot deduce that information. I cannot really deduce a char an instance of num. So it doesn't work because we use lens prime, which that does not allow us to change the type of both the structure and the focus. But if we implement first using the lens that we just learned, you remember the stop? Here the S, the initial structure is a tuple AC. The resulting structure when we're going to set things is BC. So we are changing from A to B. And we can implement this. And now we have, well, the view stayed the same. We can still call the first and see the 10. We can use the set as we used it before, but now we can set a string and we can change the resulting structure. It's no longer a tuple of 2 ints. Now it's a tuple of a string and an integer. And that's the only sort of semantical difference between lens prime and lens. Will that work for our data types? Yes, it will. So, let's imagine that we have a truck of A, and so the truck has a name and has a cargo, and so cargo is parameterized by A. We derive show and generic, and so we have 2 different types of cargo. There's fruits and electronics. Fruits can be apples or oranges, and electronics could be computer or phone. I could have a truck, Tom, which holds an apple, a single apple. I have a truck that will hold a single apple, and now I can say truck hash cargo set to phone, And this now I used to have a truck, used to be of a type truck fruit. But now what I get back in return is a truck of electronic. So there are other few nice combinations that we have in the lens library. So imagine that I have a truck full of apples, right? And I would like to add apples and oranges, and I would like to add a few more fruits to that truck. With the combinations that we saw so far, we know that I can actually do it well using set and get. So I could say, you know what, truck, cargo, set to, but now I want to add a few more fruits to it. So I need to view the original cargo and then append a list of fruits. This is doable, but I would say not necessarily very, very nice. It's like a really imperative one more time, and also not really performant, because if that lens, that cargo is, right now the cargo is really simple lens. But if it was something more complex that traversed more things, we would have to first traverse that lens to get the actual value at the beginning and also traverse it while setting it. So it's not really performant. So what we got from lens is a function called over with its operator percentage and this squiggly thing. So now I can say, so over is, instead of taking a thing that I want to say, set, it takes a function from and the function that goes from the original thing to a new thing. So I say, well, from truck, take cargo, and now over, and I provide a function, what should happen with the original fruits? When I'm saying, well, to the fruits that we have right now, append orange and apple. And there's also, because somebody saw that this has happened so often, well, for different things, you have different operators, different functions. So for example, there is append function that you can run on your lens with its own operator, and it does exactly what the one above did, and that just does in one step for you. It's more declarative, right? You sort of know it will append that list to the original list. And as you can see, I hope from this example, there is this way of understanding those operators. So this squiggly means we're setting, and different characters in front of it will give us an information like how we're setting things. So percentage always means the function, most likely lesser greater, it almost looks like a lesser greater from append. So you kind of might get what it does. Here you have another example where, for example, instead of running a function over taking a cargo size and adding 1 to it, we can just say plus squiggly 1, and it will just append 1 or multiply it. And as I said, the number of combinators is tremendous, and we'll not go over all of them. What are the other optics? Well, there are tons of them, and we have no way of covering all of that during this one single presentation. But what I was hoping to show is we've seen that lens, sort of the original data type lens stop. Hopefully we saw it solves the problem of a record syntax in a very nice declarative way. But along the way, other optics were born, and they go beyond that original problem. They provide so much more new stuff. And there's no way I could cover all of that. Probably there could be a follow-up presentation on it, or you can read a book. I think there are 2 already right now available, and some other presentations. But let me show you just the initial idea of how you could use lenses with further more complex examples. So there is another type called traversal. So traversal step means lens allowed you to focus on a single element A in the structure S. Traversal allows you to focus on multiple elements of type A in the structure S. While in lens, you knew the thing of a type A must exist. There's no way it doesn't. Whereas in traversal, you potentially might get many A's, but also none. So just to give you an example, remember how we have a list of speakers. If now I would like to get list of all the last names of all the speakers, I could just use that little combinator. So from Haskell love, I go to speakers. That is a list on which I can call traversed. So this is a lens that's, a traversal that's built into the library itself. But that gives you ability to focus just on a single speaker. Before traverse, if we just had lenses, after calling hash speakers dot, I could only do something with a list of speakers, like a single argument. But here I can just focus on like this little tiny bit, just on one speaker from that whole list. And then I can continue with lenses. I can say, well, the hash name dot hash last name. And that gives me the list of all last names from the conference. You will see the difference here is the operator that I used was not the original view that I used before, because the original view just does, well, it almost does the same thing, but sort of like combine the results together. And the reason it works this way is because if you use, it sort of leaks the abstraction. And maybe if I have time, maybe during Q&A, I can actually show how that leaks that abstraction. But if you just use the normal view, it requires for the elements to be monoid. Just so happens the string has a monoid, so it can combine two strings together into one huge string. But if we were just to get the list of all the last elements, we would just use a different operator, a different view that's defined for traversals with the one that you see in the second example. Okay. What else we can do? Like we can see if there any speaker on that list is ready. There is a function any of. So it's a function that takes a traversal, a predicate, a structure, and it goes through all the focuses, runs this predicate function on it. And if any of those elements pass that predicate, if the predicate returns true, our overall function returns true. So here in this example, I can say any of. The traversal will be speakers traverse slides ready. So I'm just focusing on the Boolean value, whether your slides are ready. The predicate is ID, so it just takes a Boolean and returns that Boolean, and I run it on Haskell love. And as you can see, there is at least one speaker who says he's ready, and I think that's matching because that's never me. Well, as you remember, I would love to change that information because I think no one is ever ready. We could do it with just lenses, right? Without using traversals. Well, we could just say modify speakers and then flat map over it and set slides to false. I guess, yeah, doable, but it's sort of, we are moving away from the declarative word. I would just like to say, well, give me a speaker, give me his list, his attribute slides ready, and just change it to false. So we can use traversed to modify stuff the same way that we use that for lenses. I can say speakers traverse slides ready, set it to false, and I get exactly what I asked for. This is very declarative in its nature. I don't really have to see how those things traverse over those structures. I'm just saying what I want, and I get the results back. Okay. So now, we have, I think 15 minutes. Armando, maybe you could correct me if I'm wrong, but I think it's 15 minutes. So let's reveal the magic.
15 minutes.
Nobody is correct, and whoever is doing the video for YouTube. All right, magic. All right. So well, there are two things we would have to answer our questions, and we will just focusing on lens. We will not be looking at traversal. So, well, maybe we can during Q&A if somebody's interested. But we have to answer two questions. How do we encode a getter and setter in a single type? And most importantly, how on earth we can use dot to compose lens together? Like, this is bizarre. This is weird. So let's look at it. Okay, so the easiest way that we could implement lens is well, since it needs to encode getter and setter, we could just give it getter and setter, the view function and the set function. So now you get, with that data type defined, you get two functions for free. One function that goes from lens, that function view that takes a lens, a structure S, and give you an A. The other function will be a function set that takes a lens, the structure S, the new value B, and gives you the T back. And as you remember, for performance, we also need that over function. So a function that takes a lens and a modification function from A to B and gives us back a function from S to T. And yeah, this is doable. Like, you can implement this. As you can see, just take my word for it, it compiles. This is nothing really magical. Like, we said lens will be getter and setter, we get getter and setter, and we also implemented over using both the getter and the setter. And as it was in lenses before, we could say lens prime SA is just lens SSAA. Okay, this works. But then again, that dot thing, right? Like, how on earth, how does it work? Well, in order for the dot, which is a function composition, to work, lens would have to be a function, a single function. Now, lens is two functions closed over one single data type in a single constructor. If you look at this code intensively, you will see that, well, we could potentially define lens as a single function because both the view and set function from B to T. So we could combine those two functions into one function. So a function that takes S and returns us a tuple, so an A, but also a modification function from B to T. And having that, we could just define lens as a type alias. So we could just unwrap it and just say lens is a type alias from S to that tuple. But there's no way this will compose, right? It cannot. How could it? So we got that far, but that's it. That's pretty much it. How could we compose that using something else? Yes, we could write the composition function. It would be very inefficient, but we could do it. But it still wouldn't be able to use the dot operator. Okay, so brace yourself. We're gonna see right now the definition of lens as it is in the library. So that's it. And when I first saw it, I was like, what? Like, wait, what? Because it's saying, okay, so for functors, so it takes a function from A to some FB, all right? So that's maybe a getter, but then it takes a structure and gives me an F of T. What the hell is that? Like, what? Okay, let's try to unwrap this. Let's see first if it actually can compose, maybe using that dot operator. And if you look at, we have two lenses, right? That one goes from conference to organizer, and the other one from organizer to contact. If we unwrap the definition of it, the first one is a function that for all functors F goes. If you have a function from organizer to F organizer, I get a function that goes from conference to conference. It kind of makes sense. It means that if I know how to modify an organizer, I will know how to modify conference. The other one is similar. If I know how to modify contact information, I will know how to modify the organizer, okay? And we see that they are in alignment, right? If I provide to a contact function and first argument, which is a function that goes from contact to contact, what I get in return is a function from organizer to organizer, which is exactly what the organizer function needs, because the organizer needs a function from organizer to organizer, which would give me a function from conference to conference back. So if you look at it, at least the composition with dot makes sense, right? We just have to align things together, and at least from the slide, it should be visible that they are nicely intact and they can be composed. But then I still don't understand how on earth I could use this type to represent an over, a set, and a view. Well, Over, maybe, because it almost looks like the definition of lens without those F's. Maybe we could just get rid of them or somewhere, I guess. But how on earth would I implement view? Well, I have 7 minutes for it. Okay, so let's focus on the definition of lens. The most important thing really here is the fact that the definition of this function, it's defined for all functors, not any particular functor. It's saying choose whatever functor you want. I don't care. This thing will work. And the idea behind implementing all those three functions over set and view is to choose the right functor. If we choose the right functor, we will be able to implement all of those three functions. Let's try to see how that would work for over. So we want to implement over. Over takes a lens, takes a function that goes from A to B, and takes an original structure and should give us a modified structure. Now we know that lens, the L here, will take a function and structure as an argument. And let's say the functor for us this time, when implementing over, we're choosing the functor to be an identity type, identity functor. So here, what I'm saying is I'm calling lens. Lens is a function. It takes two arguments. I'm just calling it. The first argument is a function that starts with an A. The A is its argument. So I apply A to func. Func is a function from A to B. So I now just from A, I got to B. And then I wrap it in the identity because as you know, the L needs a function that will go from A to FB. So what I got right now here is a function that goes from A to an identity of B. And then I apply S, which means that from the definition of lens, we see that after applying this, I got an identity of T because that's what my F is. My F is an identity. So I just got the identity of T, but I need T. Well, there is a function defined for identity, which is called run identity. And run identity goes from FT to T. That's what we wanted. Okay, so over was sort of straightforward. We could implement a set using over because if you look closely, you will see that they almost have the same signature. Over just takes a modification function, and set is more like I don't care what the previous result was. I just need this to be B. So we could call over with const B. We're just saying, oh, whatever the argument A is, I don't care. It's just going to be B. And so this works. But what's troubling is view. Because view is like, wow, there's no freaking way we could do this, right? Lens, even if we look at the return values, lens eventually gives us some F of T. View should give us an A. There's no way. There's like those types don't align. Well, they do, because you have a type which is called const. And const is a really funny data type. So it is parameterized by A and B. By B is completely phantom. You define it when you define the type, but you don't use it in your constructor. In constructor, you just wrap over A. So you can define functor for const, but this functor will completely ignore the B because there is no B in the constructor, right? That only holds the V value, and that's only what we can have. So if we implement view while calling lens, but setting the functor F to be const, magical thing happens. So really quickly, because now I have 3 minutes. So you call lens with const. So that gives you a const of B, and you provide S. So essentially what you got by calling your lens L, right? But if you call get in the type signature, we have T. It's a wrapper for a value. So if you get const, you get the A back, and the view just works. And then when I first saw it, I was like, and it takes time, but it really does work. Just trust me. Obviously, Edward Met, being Edward Met, like whenever he sees something which he could abstract, he will, I'd be like, oh, this is right hand extension or whatever, and just like makes everything more generic and more abstract. So this is the way how things are really implemented in lenses, but you can almost recognize what getting is, right? Like when you see getting right now, you sort of see, oh, it's like lens, but the functor was already applied and whatnot. Okay, I have 2 minutes, which is great because I need those 2 minutes. I need to, first of all, thanks Ollie for organizing this conference. I'm really hyped for the next upcoming 2 days. I think those will be awesome. And really thank you Ollie for that. Also, I need to apologize because I used image of Ollie and Martin for my examples, but I've learned from one great programmer that it's just easier to ask for forgiveness than for permission. So apologies both Martin and Ollie. Martin is a speaker at this conference. He's a really good friend, but foremost, he's a really good speaker, a really good hacker. So if you have a chance to see his presentation, I do encourage you folks to actually see it. My name is Pawel Szulc. You can find me on Twitter as an Encode Panda. So let me know if you liked it. If you have any questions, reach out. My DMs are open. I do and hope you folks will enjoy the conference. It's really amazing. There's no way, I've never seen such a great lineup in a Haskell conference before. I'm really hyped. I hope you will be as well. Thank you very much and see you on the webs.